Hi students, in this final video for online lecture 21, we are now going to introduce the ideal gas law. So what is the ideal gas equation? Well, it is a combination of all of the fundamental equations that we saw in the past video. So as you see here, Boyle's law showed us the inverse proportionality of our pressure and volume. Then with Charles' law, we saw the direct proportionality of volume and temperature and the inverse proportionality of pressure and temperature. And then finally, Avogadro's law. So what we were able to do is say that the volume is proportional to the number of moles times the temperature over the pressure. The nice part about this is that we can then go and solve for a constant. R is that constant. So R in this case is known as the ideal gas constant. This gets us to the equation PV equals nRT. Another form that I want you to be very familiar of is typically what we call the combined format. That is where we say that P1 times V1 over T1 is actually equal to nR. And if we don't change the number of moles and our constant stays the same, we are able to change all of our other characteristic identities. So now we can say P2 V2 over T2. So that is a nice format when you know that your number of moles does not change, and because your constant is a constant, you are able to change those as you see fit. Now what we need to do is go and try an example with that. So a small bubble rises from the bottom of a lake where the temperature and the pressure are 8 degrees C and 6.4 atmospheres, to the water surface where the temperature is 25 degrees C and 1 atmosphere. Calculate the final volume in milliliters of the bubble if the initial volume was 2.1 milliliters. So what we need to do is go back to that combined form. So we have P1 V1 over T1 equals P2 V2 over T2. So now we need to go and identify our variables. So in this case, we know that temperature 1 is going to be our 8 degrees, but remember, we need to have that in our Kelvin, so we need to go and convert that. That is going to be 281 K. Our 6.4 is going to be our pressure 1, and our volume 1 is going to be our 2.1 milliliters. So now we have our temperature 2, which is our 25 degrees C. That needs to be converted to our Kelvin, and so that is going to be 298 K. Finally, for our second pressure, we have our atmospheres here, and so this will be P2. We are going and solving for V2. So V2 equals P1 V1 times T2 over T1 P2. So let us go and put those values in. So our V2 is equal to, our pressure 1 is going to be our 6.4 atmospheres. Then for our V1, as you can see in this problem, we are able to leave it in milliliters because it is going to be the only unit left standing. So finally, our T2 is going to be our 298K. So let's get our denominator, and you'll see that I need temperature 1, which was 281K. And finally, our second pressure was 1 atmosphere. So if I have done this correctly, my kelvins and kelvins will cancel, atmospheres and atmospheres, and you'll see that milliliters is the only unit left over. So if I put this into the calculator, you will see that my bubble expands to a volume of 14.3 milliliters. So now you can see that changing multiple characteristics may hurt the expansion, It may help the expansion, but this combined format is going to give you all of the necessary information that you need. One of the important things that you're going to hear about in this chapter is what we call standard temperature and pressure. That is 0 degrees C, which is 273 Kelvin, and 1 atmosphere. The reason that this is so important is that experiments showed that at STP, 1 mole of any ideal gas occupies a volume of 22.414 liters. So now, using PV equals nRT to solve for R, I am now able to go and calculate R as 0.082057 liter atmosphere mole Kelvin. So what does that mean for us? Well, that means that we can go and calculate important values using this R equation. For us, we are going to use all of our R is 0.08206. Remember that the units are liter atmosphere over mole Kelvin, and this is going to be incredibly important for us because we are going to cancel out our units in our next problem. Let's try that example. A sample of ammonia occupies 13.1 liters at 333 K and a pressure of 172.8 kilopascal. Calculate the volume of the sample at STP. This is important because while you may not feel like you have gotten a lot of information, you have gotten enough for this problem to be solved. So let us go back to our combined form of P1 V1 over T1 equals our P2 V2 over our T2. And notice that we are going to solve for volume again. So this is V2 equals P1 V1 times T2 over T1 and our pressure 2. So let us go and take a look at this. The first thing that you will notice about our first pressure is that it's in kilopascals. We need to have it in our atmospheres. So how I can do that is take my 172.8 kilopascals and divide that by 101.3 kilopascals, which will give me my atmosphere. So now I can look for volume 1, which is 13.1 liters. And now I need to go and get temperature 2, which is not directly listed, but it says STP. So standard temperature is going to be 273 Kelvin. So now I need to go and get temperature 1, which is listed at 333 K, and pressure 2, while not listed, standard pressure is going to be 1 atmosphere. It's important that your units of pressure be the same, and using this problem, they need to be in atmospheres. So if I go and do this and put this into a calculator, you will get a value of 18.3 liters. And if I look at my answers on the left, you will see that I will get answer E. So in problems such as this, while you may not feel that you're getting a lot of information, having the simple letters of STP are going to help us as we're working through our problems. So now let's go and use our ideal gas law. So sulfur hexafluoride is a colorless, odorless gas. Due to its lack of chemical reactivity, it is used as an insulator in electronic equipment. It is also used as the opposite of helium, which normally raises your voice. Sulfur hexafluoride actually gives you a real deep bass voice and has been used in demonstrations previously. Calculate the pressure in atmosphere exerted by 1.82 moles of gas in a steel vessel with a volume of 5.43 liters at approximately 70 degrees C. So now what can I do for this? Well, we're going to use PV equals nRT. So first, I need to start with my ideal gas equation, but now I am going to solve for my pressure. So pressure equals my moles times my gas constant and temperature over my volume. So in this case, I have pressure being equal to I have my number of moles, so that is going to be 1.82 moles. I need my R, so that is 0.08206 liter atmosphere mole Kelvin. And now I need my temperature, which as you can see here is 69.5 degrees C. I would have to convert that to Kelvin, and that comes to a value of 342.5 Kelvin. And then finally, I need my volume, which it says the steel container has a volume of 5.43 liters. So let's take a look real quick at all of our units. Notice that my moles and moles will cancel, my liters and liters, and finally my Kelvin and Kelvin. And you'll notice that the last remaining unit is the atmosphere. This knows that I am going and solving for the correct characteristic of our pressure. If I go and put this into the calculator, you will find out that I have a pressure of 9.42 atmospheres of pressure. This is a good answer. So another use of the ideal gas law is doing two very important calculations. The first being density. Density is mass over volume. So we can take the ideal gas law and change it slightly, allowing us to determine not only the mass in the sample, but if we know the identity of the gas, we can use its molar mass. So density would be equal to the pressure times the molar mass over RT. Because we are going to have samples that are very dispersed and have a density of grams per liter, this is how we are going to get this to work. For molar mass, it can be a little bit tougher. That is saying that the molar mass is equal to the density times RT over P. So you must know the density of the gas if given. Another way of actually doing this problem is taking our PV equals nRT and solving for our number of moles. That gives us PV over RT. And then if you know the number of grams in your value, you can take that mass, put it over the number of moles, and you will get grams per mole, which is molar mass. Both of these equations are derivatives of P equals nRT. So you can either learn them separately, you can derive them, or you can have them on a formula sheet. Just make sure you know how to use them. And that is what we're going to practice here over the next couple of examples. So let's go and calculate the density of carbon dioxide, CO2, in grams per liter at 0.990 atmospheres and 55 degrees C. Notice that it doesn't look like that I am giving you a whole lot of information about this gas. So we remember that density is equal to our mass over volume. So that means that we are going to have our pressure times our molar mass over our RT. So this is how we are going to solve for the density. So our density is going to be equal to, notice that I do have a pressure, so that pressure is going to be 0.990 atmospheres. Now I need the molar mass of our gas. In this case, we wanted to be in grams per mole because we need the unit of grams for our density. So what is the molar mass of my carbon dioxide? Well, that is 44.01 grams per mole. So now I need to put in my ideal gas constant. So that is 0.08206 liter atmosphere mole Kelvin. And then finally, I need the temperature. Notice that I have 55 degrees C. That must be converted over to our Kelvin, and you should get a value of 328 Kelvin. So let's go ahead and cancel some units. Our atmospheres and atmospheres will cancel, our moles and moles, and our Kelvin and Kelvin. Notice that you will get grams per liter, which is going to be our units that we want. So if I go and put all of these values into the calculator, I will end up with a value of 1.62 grams per liter. For our next example, we are now going to calculate the molar mass of a gas. So it says calculate the molar mass of a gas at 13.7 torr and 23 degrees C if 13.0 milligrams occupy 165 milliliters. The difficulty in this problem originally is going and doing all of the unit conversion. You must be very careful as you're doing this. So we can say that N equals PV over RT. So let's look for our pressure. Notice that my torr is not atmospheres. So what I want to do is go and divide this by 760 to get me my atmospheres. If I do that, I will get a pressure of 0.0180 atmospheres. For my volume, notice that I have it in milliliters. That must be converted to liters. So that is 0.165 liters. My R is going to be our standard constant of 0.08206 liter atmosphere mole Kelvin. And then finally, I need the temperature, which as you see here, I have as 23 degrees C, adding 273, that becomes 296 K. So if I go and cancel all of that out, you will see that I get a number of moles that is equal to 0.000122 moles of gas. So now what can I do? Well, notice that I have 13 milligrams of gas, and now I know the number of moles. So what I'm able to do is take that 13 milligrams, remember, milli meaning I need to divide by 1,000 to get to grams. So I can say that 0.013 grams of my gas is that number of moles. And if I do this math, you will see that I get a value of 106 grams per mole. If I look at my answers on the left, you will see that that coincides with answer choice B. So as you've seen in the last two examples, it's really important that you know how to derive these equations when working with the ideal gas law to calculate our density and molar mass. The last thing that we want to do for our examples today is bring back our old friend stoichiometry. So as you've heard me 1,000 times over talking about grams to moles to moles to grams, this is the last time we're actually going to bring it up because now we can start with anything we want. A solid in grams, a liquid in milliliters or concentration, and now, as you can see, we are going to use gases in liters. Once we get to moles, and if we have a gas, instead of asking for it in grams, we can now ask it for it in volume, and we will be able to use PV equals nRT. This is your last reminder that you always need to have a balanced chemical equation. So this is probably my favorite example for the entire semester. Sodium azide, NaN3, is used in our automobile airbags. The impact of the collision actually triggers an electronic decomposition of my sodium azide, and it breaks down into sodium and nitrogen gas. The nitrogen gas is actually what fills up the bag that is stored in your steering wheel or dashboard and is there to save you. Calculate the volume of N2 generated at 80 degrees C and 823 millimeters of mercury by the decomposition of 60 grams of my sodium azide. So this is going to be stoichiometry to start off until I get moles of my nitrogen, and then I can put that into my ideal gas equation. So let's go ahead and do that. We are going to start with our 60 grams of my Na N3. So seeing that I have grams, as you probably guessed, I get to go to moles. So I will have 1 mole of my sodium azide for a molar mass of 65.02 grams. And now that I have moles, I need to go to the balanced chemical equation in order to get my moles of nitrogen. So I get 3 moles of N2 for every 2 NaN3. This will now give me my moles of nitrogen gas. That value is 1.384 moles. So now, because we have a gas and it's asking for volume, we can take that number of moles, put it into our ideal gas equation, and solve for the volume. So our volume is equal to our nRT over P. So our N in this case is the moles that I just solved for, so that's 1.384 moles. Then I have my ideal gas constant, so that is 0.08206. And I need to look at my temperature. Notice that it says that it is at 80 degrees C. I add 273. That should give me 353 K. And I need to look at my pressure, and you will see that I have millimeters of mercury. So what I'm going to do in this case is take my 823 and divide it by 760 to give me my atmospheres. If I do all of this math correctly, you will see that I get a volume of approximately 37.0 liters. This is important to know how many liters that we are going to create during this reaction, because if our airbag holds 50 liters, then our airbag won't be sturdy enough to save someone as they're going forward. However, if we build an airbag with only 30 liters of space and we make 37 liters, the airbag will explode upon the expansion of the gas and you'll actually won't be saved. This is all math that has been critically done by the automotive industry to make sure that it is catching you properly in the case of an accident. Our last example of today is going to be taking and synthesizing methanol. Methanol can be synthesized by the following reaction. What volume of hydrogen gas in liters is required to synthesize 6.80 grams of methanol at 99.7 kilopascal and 86 degrees C? So what we need to do first is go and get our grams of methanol to go and calculate the moles that we need of our hydrogen gas. So I will start with my 6.80 grams of my CH3OH, and I will go once again from grams to moles. The molar mass of my methanol is 32.042 grams per mole. And then using the balanced chemical equation, I will get 2 hydrogen gases for every 1 CH3OH. If I do this correctly, you will see that I will get 0.424 moles of hydrogen gas. So now, because it is a gas and I'm given the ideal gas equation characteristics, now I can go and solve for the volume. Volume equals my nRT over P. So I have my number of moles. That is going to be 0.424 moles. We're going to use our ideal gas constant again at 0.08206. And our temperature is stated as 86 degrees. Well, we now need to go and convert that. So that is going to be a value of 359 Kelvin. And finally, our pressure. Remember that we need to get to atmospheres. So what we need to do is go and take our 99.7 kilopascals and divide that by 101.3 kilopascals per atmosphere. So if I were to go and do all of this math For my volume, you will see that I get a value of 12.7 liters. If I were to look at my answer choices on the left, you will now see that that comes out to answer B. In this video, as long as it seems, is a very critical video when dealing with gaseous behavior. The ideal gas law not only can be used with a single individual gas or change of a single individual gas, but now you can see how we are going to use it to calculate density, molar mass, and utilize it when we are dealing with stoichiometry. Make sure you're working at all of these different types of problems. Have a great day.